recording. Audio is on. Okay. Okay, so hello everyone. Welcome to the third lecture in the series. So to summarize what we did last week, I think to summarize it would be to say that we solved the Schrödinger equation. So we started with Schrödinger equation. The Schrödinger equation was as I tried to explain, it was an implicit definition of a quantum state. So we don't like that. Why not be explicit? So we found like a formal solution to the Schrödinger equation, which revealed that the state is we have it here somewhere. There is this component to the state. Oh, here it is. So the quantum state is generated by this operator that takes some given state representing initial condition and evolves it in time to the state at some point t. So from this we can identify what is the real governor of the dynamics in quantum systems. Then this evolution operator u, which is generated by the Hamiltonian. So this is the connection between the model of dynamical laws in our system and the action of those dynamical laws. So we discussed some details about it. For one, how to interpret a function of an operator. For two, I listed like two basic properties that will be useful, and they will come in, we'll be using them all the time. So one was the composition rule, that you have a evolution in some period of time, but you can like slice it into intervals, and this, the same result will come out of it. The other one was that evolution operator is a unitary operator. So there's like you can send evolution forward in time, and you can undo it, right? So because evolution operator of minus time is an inverse of the evolution operator for plus time, right? So there is this property that can go forward and backwards. And to prove unitarity, there was an assignment to do it just algebraically, but I did a trick where I considered a dual Schrödinger equation. Some question? Okay. So I gave you a promise that I will explain what the dual space is, right? Or more precisely, what those bras are, bras and cats, right? It was mainly for the benefit of Pamela. She's not here, so disappointing. But anyway, we can say a couple of things about this. So before we proceed next, this is to finish this off. I want to talk a couple of minutes about dual spaces and bracket notation. So let me entitle this. So in the notes, we are here. So again, black vertical line, skippable if you don't need this. Okay, so to finish this off, so dual space and bracket notation. So, when I was talking about vector spaces in general, I was like, to denote vectors, I used arrow, which is like maybe a standard way of doing it. But we noticed, of course, that for some reason in quantum mechanics, we are using this kind of notation, a ket notation. Well, what's going on here? What's wrong with the arrow? Well, the idea behind this notation is like you are using, because inner products, right? Inner products. Okay, we are working in a Hilbert space. So we have vectors, but there is also inner product. And it's standard, and quantum mechanical notation for inner product is this Bra-Ket, right? So they came up with this idea. Okay, this is Bra-Ket, right? So this is Bra, and this is Ket. Okay, so it's like to remind us that we are working in Hilbert space. To give you a perspective on that, at the time this notation was invented, Hilbert space, you might think of Hilbert space probably like 7,000 years ago, ancient Sumerians or someone invented Hilbert spaces, right? Or something like that. No, this is like quite an, it's 20th century invention, maybe not invention, but the people started to, looking at it and investigating. So it's like, so at the time it was a novel thing. Heck, even matrices, matrices, everybody knows matrices, but it's like also, like 1920s or something, invention. It's like, those things are not so old. So, so people wanted to, so they came up with this idea that, okay, we have to remind ourselves that we are in the Hilbert space, so the inner product is there. So why not carry the inner product on our backs all the time? So that's why they said, okay, so vectors will be kets to remind us that this is a part of a Bra-Ket, right? But if there is a ket, there should be a bra. What is bra? So the idea was that, so if you, so this is ket and bra. The idea was that we are used to, or at least maybe we are used to using like linear operators, right? Where we like act on vectors by like multiplying. We are doing this stuff, A on ket, right? We are used to this kind of structure in our head. So they came up, okay, what if bra was also a thing that acts on the vectors to produce the inner product, right? So okay, can we think of this guy as some kind of linear, maybe not operator, but a map? Exactly, a functional. It's not an operator, because operators act on vectors and spit out vectors, right? And this guy is supposed to act on vectors, but it will spit out a number because it's it's a inner product gives you numbers. So in other words, what they tried to achieve with this notation is like to think of this, that there is a bra, and it's like acts on a ket, okay, and it gives you the result of the inner product. That's the idea. So basically, what they are saying, that bra is a map that takes vectors from Hilbert space, and sends them to inner product with this argument fixed, which is a, so this is what bra is supposed to represent. It's like you said, the functional of the or as we will get there, a dual vectors, elements of dual space. So these maps, these bras, they are indeed vectors because a linear combination of bras is a bra. And if you remember vector space, the basic definition is that you can add them, you can multiply by scalars, and you don't get kicked out of your space, right? And then this is, you can easily check that they are vectors. Bras are vectors, because if I take some z1, 1 plus z2, this, okay, and you know, this is like so Bra is supposed to represent like an inner product with a open slot. Yes?
So this inner product, the answer, should it be a complex number or should it be an element of the field, which happens to be a complex number?
Element of the field.
Yeah, element
Field.
of the field.
Okay.
But in quantum mechanics, the field is complex numbers.
Okay.
Bracket notation is, I mean, you can adapt it for any problem, and it's very useful often.
Okay.
But traditionally, bracket notation is for quantum mechanics. The field is not some weird stuff. Yeah, but in general,
It's a field. Okay.
yeah, it's a field. Oops, excuse me. Can I mute this? Sorry, I forgot to mute. So to show that this linearity, so let me like, so let's open the slot here, okay, to remind this is the map, right? It waits for an argument. It waits for some vector to put into the, put here, right? But when you look at this from this perspective, it's quite, you know, the inner product is linear, right? So that's, we discussed it previously. So in other words, I can like absorb it into one inner product. Although, because this is the left slot we are talking about, we have to pay with asterisk, with a conjugate. Right, something like this. However, this is, you know, linear combination of vectors. So this is just some vector, aka this is a bra, again a bra, because psi prime equals z1 psi 1 plus z2 psi 2 is an element of Hilbert space. So this is enough to show that this is a vector. So they form, the set of bras form a vector space. And in algebra, I hope this is true, they call it a dual space. Okay, and elements, those vectors, those bras are dual vectors. Dual to Kets, I guess. So that's the, so this is the origin of this notation to remind us that this is Hilbert space with inner product. That's why, you know, you carry the pieces of Bra-Ket on your back, and it also like treats the dual vector, the bra, as a something that acts on vectors, which also justifies the notation I've been kind of sneaking in. That you know, if you have a something like this, so you have inner product of between, and this would be some linear operator. So you have inner product between phi and the psi on which you act with some linear operator A. I was writing it like this, right? This is why this is the power of bracket notation, because you think of it as like, okay, so A acts on psi, and then bra acts on the thing here. Okay, so you can just, it's just another multiplication. Okay, maybe it's nothing spectacular at this point, but wait a bit, because this is Bra-Ket, but there is also Ket bra, right? There's so much good stuff comes from this kind of way of writing this. And one last thing to explain myself, to explain that this trick we were using here, you know, why, how come switching to this dual space is achieved by daggering everything? How come? What's going on here? So to justify the this kind of relation where you have z1 bless you a1 b1 and some psi 1 plus Z2, A2, B2, psi 2. To justify that, take this combination when dagger equals Z1 conjugate, bra psi 1, B1 dagger, A1 dagger, P2 dagger, A1, A2, sorry, dagger. Right, so you see that taking a dagger not only flips bras into cats, not only daggers the operators, but also the order is reversed, right? How do you justify this? Well, that's basically, if you abuse definition of Hermitian conjugate a little bit, this is where you get this rule. So if you, at the very beginning, I was kind of explaining that that the dagger, so if you define an operator, a dagger, this is defined by this relation with inner product. That a dagger is such an operator that taking this kind of inner product equals psi a phi. Maybe you can write it like this. Okay, that this is the operator that satisfies this equation. So you can kind of abuse this notation a little bit and say okay, so this relation that psi dagger is bra of psi. You can say okay, so this is because if I take inner product psi and let me say the dagger psi, it's supposed to be equal to psi phi. Okay, this is how you come up with this idea. That daggering psi, daggering the cat gives you bra. Okay, I don't know. I was thinking how to like explain it more. What can I say? What can I draw here? But I don't know. This is from this you have to be able to deduce this from this inscription.
I figure there's a way to use Riesz representation theorem to to like deduce that the representing element is itself the dagger of the normal, right?
I mean, I'm sure there is a like very formalistic way to like to show this, but I'm not competent enough to do it actually. So it's like for me it's more. I look at the picture, neurons fire, and like okay, that's fine. I understand what's going on. And also by doing this shenanigans with this daggering, you can also well maybe I'll write it because to explain this mystery why this got reversed. You know, we have AB and now is BA. What is going on here? This also, of course, comes from this kind of definition, right? You just have to play around with things a little bit. So for example, you could write like on the one hand, you know, like B acting on psi. It's some, you know, it's a vector. So we can write it that this is B on ket of representing the result of action of operator B on psi. And we know that from our from this, you know that this guy is a dagger of bra associated with this guy. Okay, so this is on one hand this is true. On the other hand, you can write like B psi, this inner product with phi. You can write it like this, and from the definition of Hermitian conjugate, this, oh, there should be some star somewhere. I forgot about it. This is psi of B dagger on phi. And the conjugate. So when you take this, combine it with this, you will conclude that when you take B psi and you dagger this, there will be this reversal. Can you see it here? I mean, you think about it and you will see it. I don't know how to explain it more or better.
I think there should be the star in the second line.
Yeah, because I didn't write it. Oh yeah, of course. Yeah. Sorry, I was. Yeah. Because I didn't write it in my notes, and I was like, oh, there should be a star. No, it's not there because it shouldn't be there. Yeah, exactly.
Technically, in a third line from the bottom, there shouldn't be a dagger.
Yeah, exactly.
Third line
From the bottom, but
This
sure.
Phi
And
psi
here,
dagger
5
should
shouldn't be
be-
dagger.
Yeah.
No, it is.
No.
That's the definition. What I'm trying to say. What is a dagger of psi?
Well, but it is so that if you...
Dagger of psi is such that it satisfies this equation.
no, because when you wrote the dagger of psi, it means that you are having bra, actually. Like you have a bracket there.
No.
Yeah.
Go back to corner and think about it. No. It's fine. It's fine. It's fine. You just have to see. You have to believe. You just have to believe.
You have to look long enough so that you believe it.
Many people say that it should be there. Some people say it shouldn't. It's the greatest dagger of all time. Nobody had this huge dagger, such a big dagger. We are using those daggers. And the first person to use it like this, nobody thought about it before. Yeah, I don't know. So yeah. So these are brass, these are cats, these are inner products, these are daggers. Okay, so hopefully that was I kind of explained myself a bit. Maybe it wasn't super coherent, but I don't know how to say it differently. I just those pictures. So this is how I see it. This is what I say. Okay, so that finishes our previous considerations. So we can move further, and now we will actually move to some physics. Okay, finally. So I entitled this section. I forgot if I'm using the enumeration that I use in the notes. I don't remember, but just to orientate ourselves. Quantum states in physics. That's how I entitled this section. All right, so we went this journey. First was Schrödinger equation, then we extracted from it explicit form of our quantum states, right? Okay, back up. So we started by saying this is a Schrödinger equation. This defines quantum mechanics. At least this is my Strawman picture of the typical textbook. And I was like arguing, okay, this, even though I written the Schrödinger equation for you, it's not like you can actually start doing quantum mechanics right now. You have to like decipher it first. So we started deciphering it. We figure out that it encodes what are quantum states. So we found those quantum states in explicit form. We identified the evolution operator. We talked about it and stuff like that. So now we are at the point where we have our quantum states. Quantum state is this. We have our evolution operator generated by Hamiltonian. There is some time, some initial state. So can we please do quantum mechanics? Can we do it? And you're probably not surprised that the answer is not yet. Not yet. Because you see, this is just some abstract, formal, mathematical object, right? It's not yet connected with anything outside the context of this mathematical formalism we were like showing bits and pieces of it. Because generally speaking, what differentiates a physical theory from a mathematical theory is that physical theory is composed of, generally speaking, of two like big parts. One of those parts is I call it a formalism. Capitalized. Okay. So this is like a mathematical theory part of a physical theory. Like all the maths is crammed into this category. Okay. So if we were talking about mathematical theories, that would be over. That would be all. But the physical theory has to take those abstract formal elements and connect them with something outside. So you need at least another bit to your whole theory to make it work. So this other part, I call it interpretation. Capitalized, just to distinguish it from just a word interpretation. So interpretation would be like a kind of interface between those abstract mathematical elements and the outside world. Or to put it more plainly, interpretation is it's a set of rules that defines how certain elements of the formalism should correlate or be associated with experiences of the user of the theory. And in most cases, when we say user, we mean human users, okay? The people who use those theories to make some maybe predictions about something, or maybe not prediction, maybe just for fun. But just for the sake of intellectual honesty, don't dismiss the possibility that there might be non-human users as well, right? I mean, maybe it will never happen, but it's fun to imagine. But this is kind of it's not just an academic. Well, it is an academic point, but the fact that the interpretation is like adjusted to what kind of user we are talking about means that this is like kind of it's not a set in stone thing, right? You have to adjust it for humans. The interpretation will have this and that kind of form. For like non-classical beings, maybe some quantum aliens or something, this interpretation will look very differently for let's say quantum mechanics, right? So just keep this in mind. That the interpretation is kind of adjustable. The set of rules is kind of adjustable, and it's adjusted to who is using the theory. So in other words, to start using quantum mechanics, we would have to put in something in this bucket, okay? Something that would allow us to interface this object with something that users, humans, observers can experience.
Do you want to add that this interpretation is observer dependent? Like what you experience is different from what I experience when it comes to theory, or we should feel the same thing?
Well, that's the beauty of this. This is where philosophy comes in, because these are good questions, right? How these kind of questions you have to ask yourself and try to figure out how should you answer it. In the basic the most basic way the interpretations, at least for quantum mechanics, are constructed, basically there is no distinction is made between the users, the classical observers. It's like basically one blob. There is no distinguished individuals. There is one rule to rule them all. Okay, if I can see it, you can see it, everyone can see it, and it will be the same picture will be seen. This is how it's built. Okay, the most basic construction for it, which I want to show you one of those rules. Is there something else I want to say here? Okay, does it sound clear to you? Now this kind of this is not just for quantum mechanics. Okay, I'm describing here all physical theories. Okay, if any classical theory also can be split into this kind of two parts. Although usually, if you think about some Newtonian mechanics, it's like you have your formalism, which you can think of Newton equation, put all the maps there, vectors dependent on time, and blah 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 blah. But the interpretation part for say Newtonian mechanics is like you can imagine it's very like simplistic, because it's like what is this vector r of t? The interpretation is a position of an object, and that's like you don't go beyond that. It's just this is like a primitive notion of your interpretation, because you rely on the fact that users, humans, classical beings just understand this without further explanation. So in classical theories, interpretations are usually very, very simplistic. They stop being simplistic when you go to non-classical theories. Like for example, in case of Einstein's relativity, okay, this is a non-classical theory because basically not everything can be explained in this, like by appeal to intuition. Time, for example, is like something you have to deal with. And the way Einstein figured out how to deal with this time coordinate that appears in the formalism is by introducing this measuring devices, clocks, right? It's like built around, the interpretation, the connection between formal stuff and the experiences of users is connected via some readouts of measuring devices. You don't explain how those devices work. You treat them as a primitive notion. Just, okay, clocks, everyone knows how clocks work. Hopefully, you just have to deal with it, right? And quantum mechanics is kind of, it's an extreme version of non-classical theory, because while in relativity, because in relativity, like your main object, mathematical formal object is like 4 vector, as they call it. So there's a time component, but there is like a spatial component, right? And we basically don't have to explain with anything special this R vector. Time is like the thing you have to do. Although, this is not like clear cut when you start going into details, poking stuff, but there is a measuring sticks for space. How does this work? I mean, there is a lot of interesting philosophical considerations here. But generally, you can think of relativities like time is the problem. There are clocks to deal with time. And you saw it, you heard it. And this is how it resolves to this day. Quantum mechanics is extreme because everything, there is no R. Okay, there is no, basically everything has to go through some measuring device kind of interpretation. Whole theory is built around this. And that's why it's so weird. Okay, there is basically no elements that can be interpreted by appeal to just direct intuition and understanding, at least for humans. Okay, everything has to go through some song and dance with measuring devices. And this is a point of a lot of pain for understanding quantum mechanics. The history of quantum mechanics is basically is a story of grappling with, finding the right interpretation, the right formalism, and the right way to put them together, and finding, criticizing each other. Someone proposes this and that, and someone else comes in. Here are a list of paradoxes that come up from this, and back and forth, and it's to this day is very like contentious stuff. And maybe to be more specific, what is so contentious, because when you are going for this device-based interpretation, okay, almost immediately and when you formulate the rules of interpretation, you treat your device as a primitive notion. Einstein does not explain how clocks work, just requires that they can be synchronized. That's all he needs, okay? And almost immediately after that, the questions arises, okay, but you don't explain how they are built, but can they actually be built, those devices? Or is it just a fantasy? It's just nonsense, because this kind of clocks that can be synchronized don't exist, cannot be used by humans and stuff like that. So like basically the first thing that followed the proposal of theory of relativity was, okay, so let us check if those clocks can exist. Let us try to build a model of those clocks, of those measuring devices. Einstein doesn't tell us, defines them, he doesn't define them, but we can try to, model them in some way in our theory and see if it works as he wants it to work. And this is one of the first results in theory of relativity, was a model of clock. This mirrors that bounce the light pulses from each other, and it's the synchronization can be shown that it's achievable, and this model is so convincing that people accepted this whole idea of using devices as an interpretation. And even to this day, this synchronization of this kind of clocks, this procedure that people invented to model it, to this day it's used in, basic idea is used in like synchronization of GPS satellites and stuff like that. So it's a very useful activity to undertake, right? But with quantum mechanics, what's the pain point is that this measurement problem, that is modeling measuring devices, is to this day unsolved. It's not even close. I mean, some people believe they have better ideas than others, but in general, there is no consensus. There are problems everywhere. But, this is what we have. This is how we have to live with it. So devices, measuring devices, this is our tool of interpreting what quantum mechanics does for us. What can we see? What can we predict with it? Okay. So yes, I just checked the time. Okay, good.
So, is there any experiments which actually tells that our quantum mechanics is wrong? Because if not, then why is the measurement issue a big problem?
Well,
Assuming that we believe that experiments are the kind of truth. So
well, I mean, this is like I can answer this on a couple of levels, because now imagine, look, the interpretation has elements that tell you, define the rules how to take, how to construct predictions, right? So basically, this is a set of rules that tells you what can be observed. I mean, at least some things that should be seen in experiments. But as a byproduct, it also like defines what kind of experiments are like kind of acceptable, right? So it's so if you do experiments that follow all the rules, that you have defined, right? It might be like by definition, basically impossible to not agree with them, right? So it's like it's not so easy to like this argument. Oh, everything can be just let's go to laboratory and do some stuff. This is not the easiest. It's not so simple as to use this argument to like criticize interpretation and stuff like that.
So you are telling that the experiment might have some regimes which if does not follow your theoretical models can end up having some
because look, the devices, measuring devices, right? We don't really have good models of them. So how, when you are doing experiment with quantum systems, how do you know if this is a measuring device, or maybe this is a measuring device? What is the standard to decide, right? What is an observer, right? And the answer to this is that there is no standard. It's a vibes thing. Experimental is just, well, this is not a device, but if this machine that does ping is a device, is a measuring device. Wigner friend. Wigner friend is like, it's basic. Wigner's friend is like a scenario that and well, I mean, there are a couple of ways to looking at it, but for me, it's like an encapsulation in a fun scenario, this problem of constructing a model of measuring device. Because Wigner friend is like, you have an observer who observes observing quantum system, right? So yeah, so in other words, if you want to have an observer looking at the observer observing, you would have to have some model, quantum mechanical model of observer observing. In other words, you want to have a model of measuring devices, because it's not key to have a observer, the human being with consciousness. If you have model of the device, that's fine. For Einstein theory, they didn't, the bouncing mirror didn't have a human looking at it. It wasn't necessary. And so is with quantum mechanics. So it's basically Wigner friend is a scenario. It's like a testing polygon testing field for various ideas for how to model measuring devices. Okay, because you have some idea, you put it into the scenario, and then you look for paradoxes. This is how it's the history of Wigner friend scenario is used. And every couple of years, someone comes up with a new variation, and there is like a couple of months of hot discussions, people pointing out paradoxes. Everything is fine, no, everything is wrong, blah, 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 and it's, it stops at some point and remains unresolved for the next couple of years. But Wigner friend is basically, okay, what are your ideas for modeling measuring devices inside quantum mechanics? And to this day, there are seemingly no good ideas present. I mean, good ideas were, but it's like not everyone buys it. Yeah.
Add simply that, at least for me, the main problem is where is the border, because you have quantum system, you have something interacting with it. So you write a Hamiltonian for interaction, for two quantum systems interacting. But there are some kind of fancy systems which are called measurement devices. And then when they interact with the system, instead of a unitary evolution, they cause some kind of collapses and stuff like this. Yeah? And where is the border? What makes this device, let's say the atom interacting with other atom, to be just another quantum system interacting? And what makes my detector interacting with the atom a non-quantum device, a non-quantum system, which is the device, yeah, which is performing a measurement with this celebrated collapse, say. Yeah.
So what you are talking about here, I mean, collapse is a different matter, entirely, it's not really directly related to this problem. But what you are talking about here is what's called the Heisenberg cut. Okay, and this is another is another story, which if you provoke me, I can talk about it. I can talk about it for quite a while. So if there is a if you want to hear about Heisenberg cut, no, it's just too much time. You know, not the nya, not kit, not gorba, not gorba, but cut, like with a samurai with a katana. Yeah. So this is like a Heisenberg cut. Oh my God, I'm so easily provoked. But I that would be a whole hour of me yapping about it. Maybe. I mean, on another lecture, I'm like talking more about this. Although.
So just a like question. So if you want to actually include the observer in your problem, because the Hilbert space that we are considering is just for the quantum system, right? So if you want to include the observer, we should actually extend our notion of Hilbert space to include the observer state also. So
Well, that's typically how people attack the problem, you know. So it's like, I mean, this is kind of, look, measuring device is some system. I mean, at least it should be some system, right? It's not some magic astral being, hopefully. I mean, there are people who like do it like this, you know.
I think the final observer is you, which means that if you've got a system that you included this, you need to somehow measure the system itself.
yeah, but we want to have a model for the measurement also.
Yeah,
Like the
and
device.
how do you
So
check
the
device?
yeah, but it should be consistent, right? The whole system, the whole thing should be considered together if you actually want to model anything.
Well, what you are saying, this is like one of the like attempts to explain a lot of stuff. That there is like a first person description and third person description. In the first person, you don't have to worry about this end point, right? It's like, okay, maybe the device is some quantum system in some limit, a very special quantum system. They interact with the system that is measured, and there is another system coupled to the device and another, but this is infinite regression. You will never end this. Maybe sometimes you might imagine that maybe there is some dephasing, a lot of dimension is so high that, but no, it doesn't work. So we have to like terminate it somehow. And the argument with first person description is like, I terminate it because this is what I see. And it's do, boom, fine. But this doesn't, because then Wigner friend, you're doing Wigner friend, you just, because you don't have this terminating point, it's just arbitrarily put there. There is no distinction between observer observing and some random quantum systems interacting. So it's unsatisfactory, to say the least. So it's like, it's it's super interesting and open branch of research very much. So you know, it's if you want to dig in, there is a lot of stuff to dig in.
Because like my logic was the observer plus the quantum system, that the whole world will be a closed system. And that was my logic. Yeah.
But then the issue is that, you know, what is the thing that actually makes it distinct from just two quantum system interacting? What is the thing that makes this is measuring device or not? You know, what is the criteria? And this is difficult.
For example, a sensor is just a bunch of atoms at the end, which, for example, a photodetector, it takes in a photon and releases like an electron, for example. That itself is a quantum system. Technically, when it collides with the atom and releases the electron, that's technically a quantum system. So how far do you have to zoom in before you get the detector and not a quantum system?
So by detector, you just mean that you have a system which changes its state depending on the state of another system, right? That's what you mean by a detector. So that should solve this.
what do you mean by about it? This is the whole question. What do you mean by a detector? So what is it? What is the goal? And to give you like a hint, okay? Because I thought about this for quite a while. I did some stuff in this area. So my hint is this: that the solution to measurement problem is it's intrinsically tied to the classical limit. Okay, if you understand what it means for quantum theory to go to a classical theory limit, if you specify this in a robust way, going from this is not trivial, but at least there is a good roadmap. Okay, and as it turns out, making this, what classical limit means for quantum mechanics, it's I don't think there is in the literature there's a good approach to that. Okay.
One guess from a mathematical structure is, in quantum mechanics you have the Hilbert space as your underlying math structure, and usually you are not using such a mathematical structure in classical mechanics, as far as I know. Yes. As we use it, so you need to have some understanding of, you need to come up with a Hilbert space similar structure, so that in the limit you would get the classical. I don't see any other way you can.
Alternatively, maybe it's not really a Hilbert space is not really the, because I hinted to it that interpretation depends on who is using the theory. So for humans there is one interpretation, for quantum aliens there is another interpretation. So I hinted that interpretation is an element that's for sure kind of movable, adjustable. Let's say you can rip it out, replace it with something else. But formalism is also adjustable. Reformulating physical theory is allowed and is a common occurrence, actually. In classical physics, for example, it's well known. You have like 10 different formulations for classical mechanics. You have Newtonian formulations of Hamilton. You have Lagrange. You have Jacobi, and many others. And also, quantum mechanics is also no stranger to such a thing. Second quantization. It's a reformulation of quantum mechanics. So the Hilbert, the idea, okay, so I have to find the Hilbert space of classical. Yeah, because I'm starting in Hilbert space because quantum mechanics, and like, what is the Hilbert space of classical? You see, but this might be a red herring, because maybe this is just a dead end, because you can reformulate your formalism in such a way that it's actually not. You don't have to find Hilbert. You may be formulated in a different way that's more straightforward to get to.
Hilbert space, the algebra is full of operators, and classical you don't have. So my guess would be you need to have something which the Hilbert space has, but it talks in terms of some C numbers and then ends up in classical. That's path integral. Like if you have a quantum system, yeah, and then you have like photons or something, then you can write the coherent states, and you have a path integral which is actually like C numbers, and that can. This is close. This is close.
But yeah, so it's like probably when you saw some discussions of classical limits, it's like there's a historic trajectory to that. In the very beginning, it was h bar goes to 0. That's the first, like, it's very low IQ, old school. Then it's not just h bar, so that Schrodinger equation, and the h bar goes to 0. Then was like a very obsession with Heisenberg uncertainty principle between position and momentum. They were like, Einstein and Bohr. They were like this famous discussions, Copenhagen interpretation and stuff like that. They were like drawing the devices that measure position, momentum, and you know some recoils because there is quanta of some blah blah blah, and so on. But this died out. Today nobody talks about Heisenberg uncertainty principle, and for a good reason. It's like it was a red herring, I believe. It's not the key to this mystery. But then it evolves to yeah. Then it evolves, you know, the commutation operator. Operators don't commute. C numbers commute. Classical physics use C numbers where everything commutes. So maybe it's like the limit is when you neglect commutators, and there are, you know, replace commutators with Poisson brackets.
But well, actually, all non-commuting values comes from the Heisenberg uncertainty, or Heisenberg uncertainty comes from them. So I think it is just
of which uncertainty you are thinking of.
Oh yeah,
Like,
yeah.
and have people tried, like, because now we are assuming that quantum mechanics Hilbert spaces, like that's the foundation, and we are trying to go from there. But if you want to stay mathematically consistent, another way would be to consider something which is bigger, like a new structure other than Hilbert space, which could encapsulate the classical mechanics as a subset. And but then you have to really rigorously define which subset are you working on, and so on. So
yeah. This is a very nice task. Basically, some reformulation. Consider reformulations of quantum mechanics, and maybe you can come up with one that have a nice classical limit. And by the way, to do it, you actually also have to have like some theory of classical theories, so that you know what your end goal is. So maybe some reformulations of classical theories are in order. What is the distinction? What is the fundamental difference? And can, you know, one be a limit of the other, but not necessarily the other way around? Maybe, you know, and this is very interesting stuff.
the point of that math is that one is operator oriented and other is C numbers. So I think if you can somehow solve that.
Yeah, and you can, you know, it's like, I mean, you hinted with path integrals. It's like there is a way. You know, we will be doing operators, of course, because this is like the bread and butter of actual like calculations. But this is not a fundamental thing. Let's say there are formulations that work well, but this is not the lecture about that. There is on YouTube a lecture about that if you are interested. But now let's take a break, okay? Okay, so let us carry on. We had a very nice discussion, and I'm happy that we had it. We could have it more, but let's try to keep to the schedule a little bit at least. Although you know what, schedule is, nobody will kill us if we don't, you know, if we get behind the schedule a little bit. I am happy to get behind if it means that we can talk about interesting stuff. But
what if we have some fanatic and this person will indeed kill us if we get behind this? I wouldn't be that sure.
Professor Pilansky?
Kill Lansky.
yeah, that is true. I mean, it's not true, but we can imagine that it's true, just for shits and giggles. Okay, so yeah. Okay, so I was getting to. All right, so this guy on its own, the state on its own, it's of course it's meaningless without the pad turned off. It's meaningless without interpretation. I mean, meaningful in the context of mathematical theory, but meaningless in the context of physical theory. So interpretation. So we need to put some kind of interpretation. So I'm not striving here for like complete description, definition of quantum mechanics. That's for other courses. So I will begin here with like a prototypical example of an interpretation element that we have. in quantum mechanics, and that is a Born rule. Okay, so we have a Born rule, Born rules. So just to, because there are a lot of B guys. Okay, there is Bohr. This is not the same as Born. Okay, just to remember, don't confuse those guys. Copenhagen interpretations, so-called. Bohr, Einstein discussions. This is this Bohr, Niels Bohr. Born, I don't know what Born did. Max Born? Yeah, the rule, I know the rule, that's why it's called Born, but what else? Really? I don't know. I don't know what Born is known for. No, he might be serious. I don't criticize so easily people. You know, Wigner friend, he wrote a paper, famous paper, which ponders maybe consciousness is a key element to understand quantum mechanics, human consciousness to be specific. So, you know, people try, you know, they threw at the wall everything, whatever would stick.
I mean that, you know, a cat or a dog wouldn't perform a measurement like
before humans there was nothing.
Yeah, there was the whole world was just entangled before the first human appeared on Earth.
But you know,
Don't get yourself. It's not like they really stupid people. Okay, there is like the paper is fine. Okay, he writes. This is like he's not like. Maybe we should think about it. This is like his proposition. Maybe this thing is actually. I mean, it's such a bind. It's such a difficult problem. I mean, maybe this actually is an answer. Who knows? So it's like, you know, Wigner, cool guy, clever guy. Don't. He wrote what he thought. We should, you know, don't be afraid to be cringe. Okay, to be cringe is to live, and so, you know, it's fine. It's good. So the Born rule. So before I will be able to vocalize Born rule, we have to do some preparation by explaining things about measurement. Okay, so the Born rule, the goal of the Born rule is to basically give us a prescription how to calculate a prediction of a measurement done by the user, the human, the observer, on a quantum system. So, you know, prescription for predictions of a measurement. Okay, so what do you mean? What do we mean that the measurement happened? You know, what are we predicting here? So the way to do it. So as I alluded before, measuring devices is like a primitive notion in the interpretation of relativistic theory, and the same is for quantum mechanics. So by measurement, we mean that the observer, the user, deploys. This is the kind of wording I will be using. So the observer deploys. I will be using deployment. Deploys a measuring device. The measuring device that measures certain observable. Device that measures a certain observable, and X, that's symbol X. Capital X, Y, Z, but also A, B, C, capital letter, capital Latin letter I'll be using to denote observables. So a measuring device that can be deployed to measure some observable x. I will call them x devices. So that would be x device. Okay? X device, measuring device that when deployed measures observable x. Okay. Then yeah. So there is no explanation what measuring device is, how it's built, all the details of its physical construction. These are unspecified. Okay, it's just assumed, silently assumed, that we are able to either construct such an X device or appropriate some object, some system, this cup, to use it as a measuring device. Okay. What is specified, there are two requirements we place on the measuring devices. First one, two requirements. Don't ask me to write requirements, it's just beyond my capabilities. So first one is like the measuring device, X device, it concludes its operation instantaneously. Okay, so the delay between the deployment and the conclusion of the operation of the device is negligibly short. So it's instantaneous. Maybe it's spelled like that. So the time is negligible in comparison to all the other time scales. It's localized in time. I won't be talking about space here, basically, but you can also think that's localized in space-time if you wish. But we won't be touching space. Okay, we don't need to. And the second requirement is that upon conclusion of its task, the device will display to the user single result. Single results displays a singleton result. Small x, that it's taken from some predefined set of possible results. How can I write S in this font? So it's supposed to be math BBS. Okay, I don't know how to write it, like a dollar sign. I don't know. Capital X. So the device can spit out. There is a set. We will consider finite set of discrete set of results that's chosen from a set that's characteristic for this device that measure this observable. That's why I will write that S of X, because it's characteristic to the device deployed. So it, upon conclusion, displays a result, only one result, and always some result. Okay, that's what we assume. Question?
Is it characteristic for the device or for the quantity that the device is measuring?
Excellent question. At this point, the only like a context for observables. At this point, observable is defined basically as a thing that the X device measures. Okay, it's at the moment it's not attached to anything else. So the device defines observable that it measures at the point. So why even talk about observables? Well, because along the way we will discover that it's useful to have a concept of observable and a concept of device measuring this observable, because this observable will maybe appear in some different context than just measurement. Okay, but at the moment it's just the thing that is measured by this device. So it's like a circular definition. Okay, so good question, good catch. Is there anything else? No, I think I said everything. So we don't know how they are built. We don't know how to recognize them. Yes?
The values, should it be real, complex?
Let's say that this is a subset. That's a good catch. Let's say that this is a subset of real numbers. I mean, we could be, it could be a picture. For example, this could be like maybe a flower or a kitten. But let's keep it numbers, real numbers. None of this. Because this is a thing that is communicated by the device to us. Oh, which, by the way, implicitly, the device not only does something, does it instantly, but we as humans, classical beings, we are able to read out what it displays. Okay, it kind of shows that there is this bridge between quantum and classical. Right? This device that can interface with quantum system, right? But also with a classical human that looks at it and, oh, there is a X here. At the moment, it's a device, but the device that operates between, two regimes. So it's like, okay, so what is it? We don't talk about it. Yeah, we just bought it. I don't know. I mean, it's just ping, ping. When we are more advanced, we might try. Okay, all right. Now we have some formalism, some interpretation. Now let's think about it. How can this be built? But that's a measurement problem, which is unsolved, which is a good problem to have. It was solved, nothing to see here. Okay, so deployment. So measurement is when the observer deploys X device, and this device then spits out one of the results. Always a result, always one result. So now we can vocalize Born rule. So Born rule, so maybe I will just write it down and see if I'm recording. Okay. This is this moment I go, did I press it? I am recording, very good. So to vocalize it, so the probability, probability that the deployed X device displays result X, so small x, okay, that's taken from the S of X with this set. By the way, I will call this spectrum. Okay, spectrum of the observable or of the device. That's why S. Okay. Result X given the system state at the time of the deployment so the state at the time of deployment would be some ket t. So this is the time where we deployed our device. Reads, so the probability that device deployed at time t, and the result will be x, given that the state at this time of deployment is psi, is given by the formula. This is the Born rule. So the probability, p, without hat, if you hat, it would be something else. Superscript I reserve for that is an X device, X observable. So the probability that result is X, given the state, so this is like a standard conditional probability kind of notation. And the formula is thus. So we have Bra, here we have a mysterious operator P with a hat, okay? This doesn't have a hat, so this is a number. X also, because there will be association with the observable. Argument of X, psi t, divided by norm of the state. You might say, oh, but the norm is 1. I never said that. I never said that. Yeah, I never said that anything about the norm of our states. Because I don't have to. Cannot force me. Okay, so this is the Born rule. This is the formula. This is the prediction. So when I deploy my device, it's time t, given the state, however I came to possession of that state, this knowledge. The probability that this will be ping and give me X is this. This is my prediction, and I can test it, supposedly, with the experiment, my experiences, okay? And as we can see, the state is a key ingredient in this formula, right? Everything's like an average value on the state, right? But it's not all that is required, right? There is this another mysterious for now element here, which is not explained by Schrödinger equation, stuff like that. Something new happened here, okay? So, you know, Schrödinger equation is not full quantum mechanics because it doesn't tell us anything about the Born rule, for example. There's no connection with the outside world in Schrödinger equation. So don't be fooled by people who say that, oh, quantum mechanics is Schrödinger equation. No, it's more than that. It's whole Schrödinger equation. You can forget about Schrödinger equation at all. You can live without it. So we know what this is. I mean, we know what. We have like some mathematics. We discussed what this guy is. But what is this guy? What is this other element? So as you can imagine, this is associated with the system. So this has to be associated with the chosen device and the observer, right? And this guy is a p hat x of x. So this is a projector. So if you did the Gram-Schmidt orthonormalization, the assignment, there were projectors there as well. This is the same kind of guy, okay? But those projectors, they are more general. That is, in Gram-Schmidt, we're projecting on the one-dimensional subspace, on a vector, right? These guys are also projectors, but the subspace they project onto can be more dimensional. Okay, it's like more general thing, and they don't come, and they come in a set. It's not just one. There's more of them, because this guy also have its partners. This is a whole set of orthogonal projectors associated with the device or with the observable. So this guy is an element of orthogonal projectors. Projectors. Associated, don't ask me to write associated. So as only with X, okay? So we have this set. I will use math BBP, X, because with X, association. So this is a set that's populated by this kind of dudes. such that x, the argument is of course taken from S, from the spectrum. So that's one condition. Second condition, it's a Px x prime equals Kronecker delta x prime Pxx. Okay, I will explain it in a second, because there is third condition. Sum over all x in S of our dudes here, our projectors, equals identity operator. Okay? Question?
So here you are assuming that because we just have the Hilbert space corresponding to our quantum system, and you are modeling the effect of your device as operators within this quantum system, right? That's what you're actually postulating, basically.
Yeah, that's the Bond rule, yeah. That's what we did. Or maybe...
from the device is actually coming in here in any form, right? You are still dealing with the quantum system Hilbert space. They are, right? Nothing here goes out of it. So it's still, we are just coming up with an operator which represents the device or whatever. Yeah.
Yeah, I mean, look, we're gonna complicate it maybe later a bit. Yeah, but for now, it's yeah. These are the rules. Okay. Okay. So now let me break down the conditions. So this is obvious, right? Different results from the spectrum. So there's we have projector for every result. There is something. This condition. This is actually what tells us that these are projectors and orthogonal projectors, to be more precise. Because as a matter of fact, this can be as a definition of projector. Definition of projector.
Yeah.
So the orthogonality, it follows from our assumption that you get one reading, right? Or does it have to do with anything else? Why do you need the orthogonality? Is it because we are assuming we get only one value when you look?
Why do I need? Look, I don't at this moment. Okay. No, nice. At this moment, I don't have to explain myself. Okay. I just came in. You know, I said a lot of things. You know, deployment of devices. Devices is enough. You know, you didn't question me then. Why question me now? However, you know, I'm kind of joking, but not really. This is, you know, when you construct your theory, you know, it would be nice, of course, if all the rules of interpretation, all the rules of the formalism were derived from some beautiful principle, you know, that would be nice. But equally well, they could just came to you in a dream. That's fine. Or you just guess them, whatever. As long as it works, it's you don't have to explain yourself. Okay, that's why we can. That's why we could get away with saying, "Oh, device, measuring device, primitive notion." Yeah, I don't explain what it means. I don't have to explain myself, right? So the same goes for any other rule in the interpretation. I don't really have to explain myself. However, just like measurement problem, you know, it's completely non-satisfactory, right? If you do it like that. So, like with building a model of measuring device to see if they exist, if the rules I listed are actually can be met. The dream or the belief, is my belief, is that if you make a proper model of measuring device, by examining how this model operates, you will be able to somehow justify this rule. Okay? If not, let's say you build a model and for some reason you believe that this is a good model of measuring device, but the justification doesn't come. Maybe there's you need to change it a little bit. that will be a good impulse to refine your theory, maybe. Okay, but at the moment we don't have such an impulse. We don't have this motivation to change it. So basically, I'm putting it here, and I don't really need to explain myself.
Just one more question. So, which one is more axiomatic, like the definition of projector or the bond rule? Can you get one from the other? Like
they are the same.
Okay, so they are equivalent.
They are the same, and and don't make a mistake that that is axiomatable system we are talking about. This is not an axiomatable formal system.
I would disagree because I believe projector is from the formalism, while the bond rule is the interpretation.
Well, that's
But it's an expression there. You have an expression there. I'm talking about that expression itself. So you can ask the match question that what are the rules you have to define for the projector to get that expression, right? To have certain properties. And then,
that's it is an interesting issue that the.
But you are not asking a question. What are the definition for the division line you have there? Yeah, like what is it? Yeah, it's from the formalism. The same projector is from the formalism.
I mean, this shows that the line, what is the formalism, what is the interpretation, it's rarely clear cut. Okay, you have to, especially since the way we rarely invent new theories, right? Yes, question.
That actually Hubert mentioned. When we say how this theory works, we can call it axiom, because this is almost a principle. Because without it, you cannot.
Principle, yes. Axiom, no. Axiom is something that has a definite truth value. Okay. Here, because this is connected with the observer comes in, deploys the device. You have to have like some fuzzy logic a bit. You cannot be. There has to be some give. Okay. It's not. It cannot. You cannot define. Look.
undefined terms are too much in this. That's what you roughly mean, right? By axiom, you mean you start from there and there won't be any confusion regarding what they are and so on.
Axiom is something, axiomatable formal systems, the axiom is something that you put there, is well defined, concretely defined, unmovable, and its value is set, true value is set. Here you cannot do that because you are dealing with an outside world, basically. It's like, you cannot have a laws, codex of laws that does not require any interpretation. Judiciary system is because there are no rules. You cannot define rules that cover everything in the real world, right? So this is the thing you have to understand, that there is no way to have a physical theory that's axiomatable, because you can axiomatize the formal part, some mathematics of Hilbert space. You can axiomatize that, but because you have to have an interface with outside world, this tells you that you cannot have axioms there. Okay.
But at the same time, I feel like quite often the interpretation part, like if a mathematician looks at the physical theory, interpretation might be seen as then as set of axioms for the.
For example, here we have an input, we have an output, and the way that this input goes to output is an axiom. Like this is how theory works, right?
You might, and people often pose it like that, and this is an error, it's a mistake. It's not true. It's not an axiom. It's not axiomatable formal system. So, for example, Gödel theorem cannot apply here. No Gödel theorem. Okay, well, that's too deep into it. Okay, no. It's don't be fooled by this. There are textbooks, I know a couple, but they start by axioms of quantum mechanics, and the axioms are formulated. Oh, the measurement is represented by observable is represented. This is not it doesn't have a definite meaning, this kind of sentence. If you think it does, it's because you have no clue how philosophy works. Okay? Mathematical sentences, I mean, there are languages, formal logic, where you can have, definite statements, at least in certain contexts, you close it into a certain context, but not if you if you have to use real words. I mean, it's the logic becomes fuzzy. So that, and you cannot do physics without this allowance for this fuzziness. If you think you can, you are fooling yourself. It's just not true. And at best, you are fooling yourself. At worst, you're hindering yourself. You're actually you're shooting yourself in the foot. There has to be some give, okay, on this side. Mathematics, I mean, sometimes people even allow for mathematical part, formal part, to have some give. But that's you might strive for having like perfectly consistent formal part. But again, the border between formal and interpretation is not always clear cut. Especially since if you could create your new theory, you might strive to have like very precise division between what is interpretation, what is formalism, and stuff like that. But we are given a theory, we analyze it, and it's a mess. Okay, it's a mess. I'm like using very deliberate language here, deliberate words here and there, but this is because it's not. You won't find it in the textbook. In average textbook, in average mind of a quantum mechanic, it's a mess. It's all a mess. I'm like, I filter it for you. Okay, so it's like, have to have this in mind that there is some give here and there. Okay, you have to use your judgment. Okay, look. Oh, Jesus. I'm easily provoked, and thus I was provoked. Let me finish the projectors here, because the colleagues want to take the room after us. I messed up so much. So let me just break down this, what I started to saying. So the formal definition of a projection operator, I mean, informal is that you have a vector, you act with some projector, and like there is a part of the vector that this projector will just leave alone, leave it as it be, and the rest will be deleted. This is like informal. Formal definition is that the projector is nilpotent, idempotent, thank you. That is, any operator that has this property is a projector. Very easy to check, right? And all that is needed.
Does the orthonormality of the projectors follow from the idempotent?
No. Because this is one projector. The rest, the orthogonality is a relation between others.
Okay, so does the orthogonality follow from the idempotency and the resolution to
not exactly. So I mean, any operator P is a projector when it satisfies this condition. Okay, each guy here, if you take this condition, if you take x prime to be the same, it's of this form. Okay. If I take px x delta is 1, right? And I get px. So this tells me that this is a projector.
Yeah, but you cannot say that. Yeah, you have to, that you're defining orthogonal projectors, that line is your defining property, right?
Well, orthogonal projector is just a
If I take
property of the set of projectors. It's
If
not
I
a property of the projector.
P square P doesn't mean that you have the other way around, right? That's what I was confused.
This is a set of projectors with extra bits, with extra properties. But the extra properties that they are orthogonal and they complete. Yes, so that the mode where you set x prime equal gives you, means, okay, so I'm dealing with projectors for every x, right? But when I take different, this is what orthogonality means, because if I first act with x prime, right, I'm doing the projection. So I delete everything except for the subspace labeled with x prime. Then I act with another guy, and it gives me 0, meaning that whatever this x guy, not x prime, was projecting on was not in x prime subspace, right? And since so this is orthogonality, okay? The last bit, this tells us that this is a complete set in the sense that the subspaces that each projector projects on cover the whole Hilbert space, okay? So this is like a basis, basically, kind of. It's not exactly basis, but it's associated with basis.
It does form a vector space, the projectors.
But it's not a basis in vector space. Projectors. That's not
Are you sure?
Yes.
I don't know.
Coherence is also included.
Okay.
There are more. Because this is
Yeah, okay, you're right. Yes.
The dimensions. This completeness also ensures that this is a probability and is properly normalized, right? Because I sum over x, I won't do the algebra here. I enter with the sum here, I do the sum, this turns into identity, and I have inner product divided by itself 1, properly normalized. And physically, it's connected with the fact that we always have some readout. Okay? There is no blind, or that would be extra bits if you wanted to have an option that detector is full, nothing happened. Okay, just, oh, I'm waiting. That's not what we are doing. This is like an active deployment, and it does something always. Yes. Whether it's sensible or not, that's for further inspection. And we have to finish this, and this is a spot where I can do it. Just see if yeah, okay. Well, we can live with that. This I don't want to talk about. Yeah, but I think it was kind of cool, right?
When you go from the whole space into subspace, you do not destroy the other subspace in the world of collapse.
What's collapse? I haven't seen a collapse. What are you talking about?
When you project the entire space into just one subspace, what happens with
collapse,
other subspaces?
when we go to the sequential measurements, then you can ask about collapse. Right now, there is no reason to ask about collapse. Okay.